AI finally decoded whale language. The first message shocked scientists. 30 million years before humans wrote their first word, something was already speaking in the dark. Not grunting, not signaling, speaking. In a structured, rule-based, phonetically complex language, one click at a time. A mile below the surface of the ocean, we had no idea. Then, in 2020, an artificial intelligence processed 9,000 recordings from sperm whales living off the Caribbean island of Dominica. What it found forced a room full of MIT researchers into complete silence. Not because the data was confusing, but because it was unmistakably clear. The whales had vowels, not vowel-like sounds. Not rough approximations, acoustically identical matches to the structural building blocks of human speech, the same phonetic fingerprints, in a creature that hasn't shared an evolutionary ancestor with us for over 300 million years. This is not a story about animals being smarter than we thought. That framing is far too small. This is the story of how a single AI discovery collapsed one of the most fundamental assumptions in the history of biology, and what the first decoded message actually said. Section 1. The assumption that held for decades. For most of the 20th century, sperm whale communication was considered a solved problem. Scientists had cataloged roughly 21 distinct click patterns called codas.
Here's an example of their vocalizations. They communicate with bursts of 3 to 10 clicks called codas, which are characterized by the timing separating successive clicks.
Each coda was treated as a fixed unit, a single signal with a single meaning. Think of it exactly like a traffic light. Red, green, yellow. Finite options. Zero flexibility. You cannot combine them to say something new. That model was tidy. It fit the existing framework for how animal communication was understood to work, and for decades, nobody seriously questioned it. The problem wasn't that researchers weren't listening. They were. The problem was they were listening the wrong way, treating the clicks like a menu of preset commands rather than what they actually turned out to be, the letters of an alphabet. The moment that cracked this open didn't happen in a lab. It happened in a hallway. Marine biologist Dr. David Gruber was at Harvard's Radcliffe Institute, headphones on, reviewing sperm whale recordings he'd collected near the Caribbean while studying jellyfish. A completely separate project. MIT cryptographer Shafi Goldwasser walked past his open office door, stopped, and said 7 words that changed the direction of the field. Have you tried using machine learning to decode it? Goldwasser spent her career breaking actual encrypted communication systems, the kind governments use to protect state secrets. Her instinct wasn't casual curiosity. It was professional pattern recognition. To someone trained to find hidden structure in coded transmissions, those clicks were not noise. They were a cipher waiting to be run through a decoder. That conversation led to a third collaborator, AI researcher Michael Bronstein, who confirmed that the deep learning architectures powering modern language models could theoretically be applied to animal vocalizations, if the training dataset was large enough. That single condition became the engine of the most ambitious marine biology project ever funded. Section 2. Building the machine to listen. In 2020, the effort became Project CETI, the Cetacean Translation Initiative, funded through the TED Audacious Project with $33 million and partnerships across MIT, Harvard, UC Berkeley, and 15 other institutions. The team chose Dominica as their base for a precise reason. This stretch of Caribbean water is one of the only places on Earth where multi-generational sperm whale families return year after year. These weren't anonymous animals. The matriarchs had names. Their social hierarchies had been mapped through decades of patient surface observation. Researchers knew who was related to who led which group, who the grandmothers were. What the team deployed there had never been used in marine biology before. Permanent hydrophone arrays were installed along migration routes, underwater microphone networks running continuously, biologger tags attached directly to whale skin via suction cup. Each carried 3 synchronized microphones engineered to isolate individual voices inside a group conversation. Alongside audio, every tag recorded GPS position, dive depth, water temperature, and body orientation to a fraction of a degree. The goal wasn't simply to hear the language, it was to capture context: who was speaking, who they were speaking to, what they were physically doing at that exact moment, and what the full acoustic environment looked like simultaneously. Every variable that could give meaning to sound was logged alongside the sound itself. 9,000 recordings went into the AI. What came back rewrote the textbooks. Section 3. What the AI actually found? The algorithm didn't identify 21 codas. It found 156, but the count was almost beside the point. What stopped researchers was what lived inside each one. Every coda had 4 independently variable components. First, tempo, the speed at which clicks arrived, carrying something resembling emotional urgency or calm. Second, rhythm, the spacing between individual clicks, tight or spread. Third, ornamentation, additional clicks embedded mid-sequence that shifted meaning the way a single inserted word flips an entire sentence. Fourth, rubato, subtle timing variations that added what researchers described as effective coloring, the acoustic equivalent of tone of voice. These weren't decorative elements, they were functional. Each component could be altered independently, then recombined, generating an expressive range that no fixed menu signal system comes close to matching. Scientists have a specific term for a communication architecture that works this way: duality of patterning. It means a finite inventory of basic units generating effectively unlimited meaning through combination and rule. Until this finding, duality of patterning was considered a uniquely human property of language. The AI just found it operating in an animal, clicking in pitch darkness under immense pressure, a mile underwater. Then, linguist Gaspar Bacos at UC Berkeley went further. Instead of analyzing coda sequences at the pattern level, he examined the acoustic geometry of individual clicks at the highest phonetic resolution available. What he found shook his field's foundational assumptions. The whales were producing vowels, specifically an A-type sound acoustically matching the A in father, an I-type sound matching the E in C, and diphthongs, gliding double vowel transitions like the oi in boy, where one vowel smoothly slides into another. His conclusion, stated plainly: in the past, researchers thought of whale communication as a kind of Morse code, but this paper shows their calls are more like very, very slow vowels. This suggests a complexity that approaches human language. To fully understand why that sentence is extraordinary, you need to understand what vowels actually require to produce. A descended larynx, specific tongue and jaw musculature, controlled airflow through a shaped resonance chamber. These anatomical features evolved in humans over millions of years, under direct selection pressure towards spoken language. Sperm whales have none of that anatomy. Their vocal system, the spermaceti organ, the phonic lips, the nasal complex, evolved for echolocation in the deep ocean. They didn't evolve toward language. They arrived at something that, when analyzed by the most advanced acoustic instruments available, is functionally identical to it through a completely separate evolutionary path, with no shared ancestor for hundreds of millions of years. The scientific term for this is convergent evolution, 2 unrelated lineages independently arriving at the same complex solution. When it happens with something as specific as vowels, there's only one interpretation that makes biological sense. Vowel-based communication isn't an accident of human anatomy, it's a signature of a certain kind of cognitive complexity, and it emerged twice, on land and in the deep ocean, completely independently. Section 4. They weren't just producing sounds, they were having conversations. Structure is not the same as meaning. The researchers knew that. What they found next moved the evidence a critical step closer. The same individual whale produced different coda patterns depending on who it was addressing. Not what it needed, but who was listening. This is called audience design. In human communication, it's the capacity that lets you speak differently to a child than to a professional colleague, or soften a message when someone is struggling. It doesn't just require language, it requires a working model of another individual's perspective, what cognitive scientists call a theory of mind. Marine biologist Shane Giro, who has spent 13 years embedded with sperm whale families in Dominica, describes exchanges that last up to an hour. Multiple whales overlap, respond, build on what was just said. There is measurable turn-taking. There are moments of simultaneous clicking, interruptions, that appear to be socially tolerated within close family groups in ways they aren't between strangers. The social architecture, visible at the surface, maps directly onto acoustic patterns measurable below. These aren't random vocalizations. They're structured around relationships. The brains sustaining those conversations are the largest of any animal on Earth, 6 times the mass of a human brain. These animals live in matrilineal families with multi-generational social structures, pass cultural traditions from grandmother to calf across centuries, and execute coordinated deep-water hunting strategies in complete darkness across hundreds of meters of open ocean. Behaviors that require real-time multi-party information exchange. Section 5. The first decoded message. Out of 156 codas, researchers have cautiously identified one specific pattern they believe they understand. It's called the 1 + 1 + 3. 2 isolated clicks, a brief pause, then 3 faster clicks in sequence. It's the most commonly documented coda across Caribbean sperm whale families. It appears across the widest range of social contexts, before deep dives, after surfacing, during group gatherings, at births. The working hypothesis. It means something close to "I am here." That's the first message. Not a warning, not a demand, just presence. One living thing confirming its existence to another. That phrase has been transmitted between sperm whales, likely millions of times, across 30 million years of ocean, in a language humans couldn't read while we were hunting them. Dr. Daniela Roos of MIT put the broader finding directly. Our results show there is much more complexity here than previously believed. This is challenging the current state of the art of beliefs about the animal world. That may be the most understated sentence in modern science. Closing. What comes next? The AI has mapped the grammar. It has not yet translated a full sentence. The phonetic inventory is confirmed, the combinatorial rules are modeled, the vowels are cataloged. What remains completely unknown is what any specific sequence encodes, and closing that gap is the entire next phase of the project. Project CETI's team is building a behavioral archive that cross-references every recorded vocalization against documented physical actions, social context, family relationships, and environmental conditions, building the correlational dataset that may eventually allow meaning to emerge from structure. Whatever that matriarch has been telling her family for 70 years, whatever warnings traveled thousands of miles through whale populations when commercial ships first entered their waters, whatever these animals have been saying to each other about the warming ocean, the disappearing prey, the noise that now saturates every basin on Earth. It was all said in a language we didn't know existed. We found the alphabet, we identified the vowels, we decoded the first word. The sentence is coming.